we're going to finish up our static electricity unit by talking about capacitors and capacitance. A capacitor is a device which stores charge. And capacitance is the ability or how well something stores charge. The letter for it is C, and the unit is farads. After Michael Faraday, who was very instrumental in figuring out electricity and magnetism. Now, the simplest type of capacitor is a set of parallel plates. If I take and hook a battery, and this is the symbol for a battery here, this is the positive side, that's the negative side. That's a battery. And I hook it up to my parallel plates. This side that took up the negative side of the battery ends up with a negative charge. This side hooked up the positive charge of the side of the battery ends up with a positive charge. And if I unhook that battery, those charges are going to stay on those two plates because the negative is going to be attracted to the positives. They're not going to want to leak off, so it'll hold the charge. Now, there are some equations that we're going to use. One is that C is E0, it's epsilon naught A over D. The E0 is a constant, it's 8.85 times 10 to the minus 12. And that's going to be on the front of the reference table. A is the area of the plates. And the bigger the area, the bigger the capacitance, and that makes sense because if the plates are bigger, you can store more charge on them. And then D is the distance between the plates. The next thing, the charge stored on a capacitor is going to equal a capacitance times the voltage. The bigger capacitance, you're going to have more charge stored on there. And the bigger the voltage you hook it up to, the more charge you're going to have on there. And then the energy stored is 1/2 CV squared. So a lot of times you're just going to be plugging into these equations to solve. So here's an example. Parallel plate capacitor has capacitance of 0.4 nanofarads. The distance between the plates is 0.02 and it's charged with an electric potential of 20 volts. So maybe we'll draw a little picture of this. Okay, so I have my parallel plates. Okay, the capacitance is 0.4 nanofarads is times 10 times 9. The distance between the plates is 0.02 meters. And the voltage across them, or the electric potential difference, is 20 volts. And then we want to find the area of the plates. So my equation that has area in it is this C is E0A over D. If I rearrange it, I would get A equals CD over E0. I did all my algebra in one step there. And C was given as 0.4 times 10 to the minus 9. The area, D, that's 0.02, and that E0 is 8.85 times 10 to the minus 12. And that's going to give me a value for the area of 0.90 meters squared. Step B, what is the electric field between the plates? We have to go to this equation, which we used before. The voltage was 20 volts and 20 meters, and that's going to give me 1,000 coulomb for the electric field. Part C, the charge stored on those plates. Q is CV. Capacitance was 0.4 times 10 to the minus 9. And the voltage is 20 volts. And that's going to give me that the Q is 8 times 10 to the minus 9 coulombs. And then for D, the energy stored in the plates is PE is 1/2 CV squared. So it's 1/2. C was 0.9 times 10 to the minus 9. And our voltage was 20. Got a number to square it. And we'll get a value of 8 times 10. Minus 8 joules of energy stored on the plates. So that was a pretty straightforward example because it was just plugging in. At the top of the next plate, we have something a little more difficult. Parabolic plate capacitor carries charge Q when connected to a battery, which supplies an electric potential difference of V. So I'm making clear on this here. So I have my parallel plates. They have voltage V, and the charge on it is Q. And what will happen, each of the following, if the capacitor remains connected to the battery, and the distance between the plates doubles. So I didn't draw the battery here, so we'll put the battery here. Okay, now, the trick is, when it says remains connected to the battery is providing the voltage. If it's a 1.5 volt battery, the voltage is going to be 1.5. If it stays connected, that means V is going to stay the same. So my electric potential difference is going to be the same. Now, capacitance. So what I'm doing, distance is doubling. So D doubles. So what equation has capacitance and distance? C is E0A over D. So the distance is on the bottom, so if the distance doubles, the capacitance is going to be half as big. What's going to happen to the charge on the plates? So now charge is Q. I can think of this. Q equals CV. If V stays the same, and we just found that the C is half as big, so therefore Q is half as large. And then the last thing it asks for is the electric field. E is V over D. Remember, V was staying the same. D doubles. So therefore, E is half as large. Now, they can ask the question differently. They can say, what happens if it's disconnected from the battery? If it's disconnected from the battery, that's going to tell me that V can change, but Q stays the same. Because if it's disconnected, there's no place for the charge to go. So charge, so I can jump down here, charge stays the same. V is going to change, and I have to figure out how. The capacitance, again, it's C equals E0A over D. If D doubles, it's going to put a 2 on the bottom, so therefore C is half as large. Now the electric potential difference, we have this equation, Q equals CV. If I rearrange it for potential difference at V, it's V is Q over C. Q stayed the same, and C is half as big. If it's a half on the bottom, that means the voltage is going to double. And then for electric field, we have E equals V over D, and the voltage doubled. But the distance also doubled, so that's going to cancel, and the electric field stays the same.